Welcome to this video on ionic versus covalent bonding. Understanding how and why atoms bond is a fundamental topic in chemistry. This video will help you master the two main types of chemical bonds. Atoms bond to become chemically stable, striving for a full outer electron shell, like noble gases. This goal is known as the noble gas rule. The type of bonding depends on the atoms involved. The two main types are ionic and covalent bonding. Ionic bonding involves the transfer of electrons between a metal and a non-metal. Covalent bonding involves sharing electrons between two non-metals. The golden rule is metal plus non-metal equals ionic, and non-metal plus non-metal equals covalent. Chapter 1 focuses on ionic bonding. This occurs when metals and non-metals combine through the transfer of electrons, forming charged ions held together by strong electrostatic forces. In ionic bonding, the metal atom loses electrons and the non-metal atom gains them. This transfer creates two oppositely charged ions which attract, forming a strong ionic bond. Metal atoms typically have few outer electrons, making it easier to lose them and form a positive ion or cation. Non-metal atoms have many outer electrons, so they gain electrons to form a negative ion or anion. The positive and negative ions are drawn together by electrostatic attraction, forming the ionic bond. A greater charge difference between the ions leads to a stronger ionic bond. Ionic bonding creates a giant, repeating three-dimensional structure called an ionic lattice. Positive and negative ions alternate in a highly ordered, repeating pattern. The cumulative effect of these bonds makes the structure very strong. Take the example of sodium chloride. Sodium, a metal, loses one electron to form Na+ ion. Chlorine, a non-metal, gains one electron to form a Cl- ion. These oppositely charged ions attract, forming sodium chloride, common table salt, in a giant ionic lattice. Sodium chloride, or sodium chloride, is a classic ionic compound. Its cubic crystal shape directly reflects its regular, repeating ionic lattice structure. This illustrates how the structure dictates the properties of the compound. The giant ionic lattice gives ionic compounds distinctive properties. The strong electrostatic forces result in very high melting and boiling points. While solids, they don't conduct electricity, but ions become free to move when dissolved or molten, allowing electrical conductivity. Despite being hard, they are brittle and shatter when struck. Chapter 2 covers covalent bonding. This is how non-metal atoms share pairs of electrons to form molecules, leading to an enormous variety of substances. In covalent bonding, atoms share pairs of electrons instead of transferring them. Each shared pair counts as a full outer shell electron for both atoms simultaneously, which allows both to achieve stability. In sharing, each atom contributes one electron to the shared pair. Atoms can share 1, 2, or 3 pairs of electrons, forming single, double, or triple bonds. More shared pairs result in stronger, shorter bonds. Covalent bonding only occurs between non-metal atoms. Since neither atom can easily give up electrons, sharing is the compromise. This process forms discrete molecules, where both atoms achieve a full outer shell simultaneously. Hydrogen and oxygen combine to form water hydrogen oxide. Each hydrogen atom needs one electron, and oxygen needs 2. Oxygen shares one pair with each hydrogen atom, forming 2 covalent bonds, giving all 3 atoms a full outer shell. Water is a classic covalent molecule, crucial to life on Earth. Its simple structure, one oxygen atom bonded to 2 hydrogen atoms, gives it remarkable properties, such as being a universal solvent. Other covalent examples include hydrogen gas, which is a diatomic molecule with a single shared pair. Methane, carbon tetrahydride, is the simplest hydrocarbon, with carbon forming 4 covalent bonds. Oxygen gas, O2, forms a strong double bond by sharing 2 pairs of electrons. Simple covalent substances have distinct properties from ionic compounds. They generally have low melting and boiling points, do not conduct electricity because they lack free charged particles, and are often insoluble in water. The key differences are: ionic bonds involve electron transfer between a metal and a non-metal to form ions, resulting in high melting points and conductivity when dissolved. Covalent bonds involve electron sharing between non-metals to form molecules, resulting in low melting points and no conductivity. To quickly identify the bonding type in an exam, remember the golden rule: metal plus non-metal equals ionic bonding. Non-metal plus non-metal equals covalent bonding. Checking the elements involved is the fastest way to the correct answer. Let's practice the rule. Magnesium oxide is metal plus non-metal, so it's ionic. Carbon dioxide and ammonia are both nonmetal plus nonmetal, so they are covalent. Sodium fluoride is metal plus nonmetal, making it ionic. This diagram visually summarizes the fundamental difference. Ionic bonding involves electron transfer to create ions that attract, while covalent bonding involves electron sharing to form a molecule where outer shells overlap. For dot and cross diagrams, use dots and crosses to show electrons from different atoms. For ionic diagrams, show the electron transfer and enclose the resulting ions in brackets with their charges. For covalent diagrams, show shared electron pairs in the overlapping region. Ionic compounds have high melting points because they are held together by thousands of strong electrostatic forces in a giant lattice. Overcoming all these forces simultaneously requires an enormous amount of energy. Covalent substances have low melting points because only the weak intermolecular forces between molecules must be overcome to melt or boil the substance. The strong covalent bonds within the molecules do not break during melting, requiring very little energy. Ionic compounds do not conduct electricity in their solid state because the ions are fixed in the lattice. However, when melted or dissolved, the ions are free to move and carry charge, allowing the compound to conduct electricity. Simple covalent substances do not conduct electricity in any state because they have neither free electrons nor free-moving ions. The rule is simple. Electrical conductivity requires free-moving charged particles. Melting points are a strong indicator of bond type. Ionic compounds like sodium chloride melt above 800 degrees Celsius. Simple covalent molecules like water and oxygen melt or boil at much lower temperatures. A melting point above 300 degrees Celsius strongly suggests ionic bonding. Knowing how to structure your answers in exams is crucial. We will now review key exam skills to help you secure every available mark on bonding questions. To describe ionic bonding for a multi-mark question, cover these points. First, state the atoms involved, a metal and a nonmetal. Second, describe the electron transfer. The metal loses electrons to form a positive ion, and the nonmetal gains electrons to form a negative ion. Third, explain the attraction. The oppositely charged ions are held by strong electrostatic attraction. Finally, mention the result. This forms a giant ionic lattice structure. These 4 points ensure you maximize your score. Similarly, describing covalent bonding requires 4 points. First, state the atoms involved, non-metal atoms. Second, describe electron sharing. A shared pair of electrons forms the bond. Third, explain why. Sharing gives both atoms a full outer shell. Fourth, name the product. Covalent bonding results in the formation of a molecule. Avoid common exam mistakes. Be precise by using transferred for ionic and shared for covalent. Remember that in covalent substances, only intermolecular forces break during melting, not the strong covalent bonds. Ionic compounds only conduct when molten or dissolved, and nonmetals form ionic bonds when reacting with metals.